Have you ever gazed up at the night sky and wondered about the mysteries that lie beyond our planet? Prepare to embark on an exhilarating journey through the depths of space, where reality becomes more captivating than fiction. Imagine a world where the laws of physics are stretched to their limits, where time and space intertwine in a cosmic dance. Today, we're diving headfirst into the enigmatic realm of black holes, where the fabric of the universe unravels before our eyes. Join us as we unravel the mind-bending conundrums that have puzzled scientists for centuries. From Isaac Newton's groundbreaking discoveries to Einstein's revolutionary theories, we'll trace the evolution of our understanding of gravity and delve into the heart of the black hole itself. But hold on to your seats, because we're about to challenge everything you thought you knew about the cosmos. Recent research suggests that the infamous singularity at the core of black holes might not be as inevitable as we once believed. Could this be the breakthrough we've been waiting for? Prepare to have your mind blown as we navigate through the twists and turns of space-time, confronting the most perplexing questions in modern physics. And don't forget to join the conversation in the comments below. We want to hear your thoughts on the wonders of the universe. So, fellow space enthusiasts, are you ready to defy the limits of human knowledge and embark on an unforgettable voyage through the cosmos? Then hit that subscribe button and join us on this extraordinary adventure into the unknown. Let's explore the universe together. Many, perhaps most physicists were seriously uncomfortable with the idea of black hole singularities, and they got even more uncomfortable when in 1965, British physicist Sir Roger Penrose showed that singularities really are unavoidable in general relativity. His Penrose singularity theorem, for which he won the 2020 Nobel Prize, claims that as long as an event horizon exists, so must a singularity. Perhaps the most important implication of the singularity theorem is to show that general relativity really is in fundamental conflict with quantum mechanics. If that's the case, then the only salvation from the paradox of the singularity is some greater theory combining quantum mechanics and general relativity, in which the singularity will evaporate away as if it was just the bad dream of ignorant 20th century physics. But just recently, we've had a ray of hope from a completely unexpected direction. In a paper released in December, Roy Kerr, one of the greatest black hole theorists of all time, may have shown that we can avoid the black hole singularity without quantum mechanics after all. In order to get to this radical new result, we need to build up some understanding, so let's refresh our knowledge of black holes and review the Penrose singularity theorem. Then maybe we can decide if Roy Kerr really did destroy the singularity. So, to start with, Roger Penrose didn't exactly prove the existence of singularities, not explicitly anyway. He demonstrated that space-time paths must terminate inside a black hole. Anything moving in space-time under only gravity follows something called a geodesic. This is a path through space-time that minimizes the combined spatial and temporal distance traveled. Before the Penrose singularity theorem, it was generally held that geodesics had no end. An object might travel along a segment of a geodesic, for example, a ball being thrown on a parabola, but the geodesic itself can be traced both backwards and forwards beyond the ball's trajectory. Forward forever into the expanding universe, or backwards to the beginning of the universe. Roger Penrose showed that inside a black hole, geodesics have to converge at the center and end there. When a space-time admits geodesics which don't go on forever, we say the space-time is geodesically incomplete. You can imagine geodesics as the grid lines of space-time, forming a smooth, if sometimes quite warped fabric on which the laws of physics work nicely. Geodesic incompleteness means there are pinched-off regions where infinities appear and the laws of physics break down. So the argument of Penrose was that geodesic incompleteness means singularity, but Kerr has an objection to the argument, and it depends on a subtle interpretation of geodesic incompleteness. So let's dig a little deeper. When Penrose said a geodesic captured by a black hole ends at the black hole center, he meant something very specific mathematically. He meant that the geodesic parameter is bounded, so the mathematical variable we use to describe the evolution of something along a geodesic terminus. Similar to how your latitude terminates if you travel to the South Pole, you can't go further south once your southness is maxed out. For the geodesics describing the paths of matter, the geodesic parameter can be, and usually is, taken to be the proper time. That's just the time measured by someone moving along that trajectory. So if the parameter for a matter geodesics is bounded, that would imply a singularity because there's no way to trace a flow of time through it. There's no meaningful way to define after the singularity in either space or time. These are dead ends in space-time. Now, Penrose constructed his argument using the paths of light, not of matter, and it turns out the difference is crucial, as we'll see. Now we have good reason to believe that essentially all real black holes have some rotation, so the Kerr solution is kind of a big deal, as is Roy Kerr. And Roy Kerr vehemently disagrees that singularities exist, nor even that the Penrose singularity theorem has anything to say about their existence. Let's finally get to the heart of his objection. As we reach the end of our journey, it's time to reflect on the mind-bending revelations we've uncovered together. From the intricacies of geodesic incompleteness to the elusive nature of singularities, we've delved deep into the heart of black holes and emerged with a newfound understanding of the universe. But our exploration doesn't end here. There's still so much left to discover, so many mysteries waiting to be unraveled. So what are your thoughts? Do you believe in the inevitability of singularities, or do you find yourself questioning the very fabric of space-time? We want to hear from you. Drop your thoughts in the comments below, and let's keep the conversation going. And don't forget to hit that subscribe button to stay updated on all our future adventures in space science. Together, we can continue to push the boundaries of human knowledge and explore the wonders of the cosmos. Thank you for joining us on this extraordinary journey, and we can't wait to see where the stars will take us next. Until next time, keep looking up